Kumar Gupta. Today we will start with our lecture series 4 for basic organic chemistry. If you remember in the lecture 3 we had done electronic effects, that is what is the effect of electron on the chemical reactivity. Then there are different types of effects like inductive effect, then mesomeric effect or resonance effect, right? Today we will do the further two effects other, that is first one is happens to be, what do you mean by electromeric effect? Electromeric effect. Electromeric effect. No. And the fourth effect is hyperconjugation. Conjugation. First we will start with electromeric effect. Now, before starting with electromeric effect, I would do some basic requirements for so that you can easily understand what you mean by electromeric effect. What happens in an organic reaction? In an organic reaction, there is something called one main organic compound which will react with some chemicals and to bring about specific changes in that particular organic compounds. For example, I'll take for example, this is R, C, double bond O, R. That means this is an ester group. This is our main organic compound. Fine. Now, this is reacted with some chemical. Take for example water. Water also is a chemical, nothing else. Water is also a chemical. It will give R, C, double bond O, OH. Right? Now, so due to the presence of water, there is a specific chemical changes brought about in ester. So these main organic compounds, they undergo a reaction in presence of a particular chemical to give the product. This is the product, which is an acid. So these main organic compounds are known as substrate. Henceforth, whenever I say substrate, that means it is a main organic compound who will be undergoing a chemical change, a chemical reactivity on that particular substrate, on that particular organic compound. And this particular chemical, or the one who is responsible for the reactivity to happen is known as reagent. I will explain you about reagent further a few minutes from now. First we will see what do you mean by substrate. As I have told you what do you mean by substrate. Now there are two types of substrate. Fine. Now the first type is nucleophilic. What do you mean by nucleophilic? Nucleo means nucleus. And philic means liking. Nucleus liking. Liking for nucleus. Nucleus, I know, in nucleus there are protons, that is, they are positively charged. They are positively charged. That means, what do you mean by nucleophilic? If they have a liking for nucleus that is positively charged, that means they itself it itself is a negatively charged species. Negatively charged species. That means a nucleophilic. It is a negatively charged species. Negatively charged species, or I can say it is an electron rich center, right? It is an electron rich center or a negatively charged species. For example, we'll see alkenes, that is C double bond C. This double bond or pi bond is nothing else but rich in electrons. It will easily react with. So this is a electron rich center. So it is a nucleophilic center. It is a electron rich center. Okay. Then we can say alkynes. Fine. Alkynes. It is again a nucleophilic, nucleus liking. It is itself a negatively charged species. Then we can say benzene. It is rich in electrons. It is rich in electrons. So I will say they are nucleophilic centers. They are nucleophilic centers. Nucleophilic centers मतलब negatively charged species या electron rich centers. Nucleophilic center or electron rich centers. I will say nucleophilic center or a electron rich center. Anything I can say. Electron rich center. Fine. Now, this is one nucleophilic. As I have told, there are two types of substrate. One type is nucleophilic. This is suppose A. Now, the second type. The second type is electrophilic. Electrophilic, nothing else but electron. Electro means electron liking. Electron liking. If it is an electron liking, then it is itself a positively charged species. Can I say? Positively charged species or electron deficient center. Deficient center. Deficient in the sense it does not has electron. Deficient means starving. Starving. Electron deficient. That means it has no electron. That means it is a positively charged species. Positively charged species. For example, we will see, take for example R C double bond O O H. Now oxygen, as we know, it is electronegative, right? O. So it will pull electron towards itself. So if it pulls electron towards itself, then this is automatically it's going to become positively charged. So I can say it is itself a positively charged species or electron, because all the electrons of this carbon has moved towards oxygen. So this is nothing but electrophilic center. Electrophilic center. Fine. Similarly, we can say ester, one and the same thing. It is also positively charged species, and many more, okay, and etc. So I think so you have understood what do you mean by electrophilic and what do you mean by nucleophilic. No. After this, we will see another one. So initially we saw substrate. Now we will see what you mean by reagent. As I told, it is a chemical added across a substrate. Across a substrate to bring about specific changes in the substrate. Specific changes in the substrate, thus forming product. Fine. So what is reagent? Means chemical added across a substrate to bring about a specific changes in the substrate, thus forming products. Now, reagents are also mainly of two types. First is nucleophile. Nucleophile means nucleus liking. That means that is liking for positively charged center. And positively charged center is known as electrophilic center. Fine. Electrophilic center. That means a nucleophile. We will indicate nucleophile as Nu minus. Minus indicates rich in electrons. Nucleus liking, which is rich in electrons. That means a nucleophile can I say a nucleophile prefers or attacks a electrophilic center. Electrophilic center that is positively charged or electron deficient. Fine. A nucleophile will always prefer or attack a electrophilic center. We have a few examples I'll tell you. Like OH. It is OH minus. Then X minus, that means halogens. X minus. Then I will say Cn minus. Cn is nitride. OH is hydroxy, Cn, and there are many more. Yeah, you can say NO2 minus. Fine. Okay, now second B will be electrophile. electrophile. As and when we go forward, we will see many more examples of nucleophile. Generally, we can say any double bonded compounds, double bonded functional group, generally double bonded functional groups. Attacker, electrophilic center, double bonded, or you can say a triple bonded, anything. That means or unsaturated. Although there are even single bonded like OH, which is also a very good nucleophile. Okay? We will see now henceforth. Now what do you mean by an electrophile? Electrophile is nothing else but electron liking. Right? Electron liking. No. It is denoted by, I'll say E plus. Electrophile. E plus. Okay? It is electron deficient. Since it is electron deficient, that is why it has a liking for electron. Electron deficient. Okay? It is electron deficient. Now, that means can I say it has a liking for, as I have told you, liking for a negatively charged center. That means a nucleophilic center. Nucleophilic center. Nucleophilic center is negatively charged. Nucleophilic center is a negatively charged. So electrophile prefers or attacks a nucleophilic center. This is very important. A electrophile will prefer a nucleophilic center and a nucleophile will prefer a electrophilic center. Fine? Right? Now. Now. Now we will see there are basically speaking two types of nucleophile. Two types of nucleophile. There are two types of nucleophile. First is a neutral. As an example, I had told you nucleophile example was OH minus, then Cn minus. Right? Now, two types of nucleophile. One will be neutral. Now, what do you mean by neutral? Neutral means a covalent compound where the central atom has a complete octet and one lone pair of electron. Right? Neutral means what? It has a covalent compound where the central atom has a complete octet and a lone pair of electron. Example, water. Water has a complete octet and a lone pair of electrons. It has lone pair of electrons. Fine. Then you can say ammonia. It has a complete octet and a lone pair of electron. Similarly, you can say alcohol. So wherever you see HOH, that means water or ammonia or alcohol, they are nucleophile but neutral nucleophile. Second will be ambident nucleophile. Ambident nucleophile. It has what do you mean by ambident nucleophile? Ambident nucleophile means it has two nucleophilic center. Two nucleophilic center. That means of which one is neutral and other is negatively charged. Species. Ambident nucleophile is one is a neutral, two nucleophilic center of which one is neutral and the other is negatively charged species. Example, C triple bond N. This is minus charge. Fine. It's negatively charged species and this is a neutral molecule, neutral atom. So this now, or else you can say O dash N double bond O. This is minus and this has a lone pair of electrons. In neutral, it is a complete octet and one lone pair of electron. Here, lone pair of electron, which is neutral, and a negatively charged species also. A negatively charged species along with a lone pair of electron. So this is ambident nucleophile. Now, as I had told in the previous slide, it was electrophile. If you remember, electrophile I had told you. Just now I had told you. What was electrophile? It was basically nothing else but liking for electrons. Liking for electrons. That means nucleophilic center. That means nucleophilic center. I'll give you some examples like H plus or CH3 plus, or you can say N double bond O single bond O minus plus. This is an electrophile. Fine. This is a electrophile. Right? Take a note of it. So you might have understood what is a nucleophile, what is an electrophile. In nucleophile, you have neutral and ambident. Right? Now, why have I taken this? Because this becomes the basis. This becomes the basis of further electronic effects. Further effects which I have to teach you. Right? That is in electronic effect. Initially we saw resonance structures, mesomeric effect, inductive effect. Now, henceforth, now another type of effects are coming. Of which the first one is electromeric effect. I can say it is a temporary effect. It's a temporary effect. And it operates in molecules. It operates in molecules having pi electrons. That is multiple bonds. That is multiple bonds. Or you can say multiple bonded compounds. Multiple bonded compounds. Multiple when attacked by nucleophile and electrophiles. That means a multiple bonded compounds when attacked by a nucleophile or an electrophile gives rise to an effect known as electromeric effect. Electromeric effect. Now, suppose in presence of an electrophile, in presence of an electrophile, electrophile I will indicate by E plus as I told you previously. Now, fine. Now, here there is a shifting of electrons like that. Shifting of electrons on the carbon atom to such that to make an adjustment where the electrophile can sit. I will like that. See. Now this electron will go and sit here, so it will become negatively charged, and this will become. Now this when attacked by an electrophile. This electrophile will, and this is positively charged, and it will require a negatively charged species. So fine. So positively charged, and here the electrophile comes and sits. Fine. Here the electrophile is added on the carbon atom, which is negatively charged, and the electrons are transferred on this carbon atom, and the electrophile sits on the same very carbon atom which gains a negatively charge, right? So this effect is also known as plus electromeric effect or plus E effect. Plus E effect. Plus E effect, because the shifting of electron happens on this carbon atom, and you can say the electron is going towards the electrophile. Negatively charged electron is going towards the electrophile, is happening in the direction of the electrophile. Since it is happening in the direction of the electrophile, so it is, you can say transfer of electrons in the direction of the electrophile or towards the electrophile. So it is known as plus E effect, right? So it is known as plus E effect. What happens in polar compounds? Polar compounds where two poles are formed, plus and minus. In polar compounds, the presence of attacking reagents, there is a complete transfer of electrons, or you can say complete transfer of electrons, or pi electrons for that matter. Electron pair. Right? In polar compounds, the polar compounds, in presence of an attacking reagent, there is a complete transfer of electrons or pi electrons. For example, I'll show you. This is, take for example, this is fine. Now, if I say this has gone here, so this will be O minus this. This is a polar compound. Now suppose this has been attacked by a nucleophile, right? A nucleophile. Take for example, I will say a nucleophile like Cn minus. Your attacking reagent is a nucleophile. Nucleophile is Cn minus. Fine. Now, what happens? This is the positively charged. To see this Cn will sit here, no doubt about it. The Cn will sit here. O minus. That means the attacking reagent is going towards the positive charge. In the previous case, the negatively charged was going towards the positively charged electrophile. Fine? Yeah. So this will be known as minus E effect, or minus E, minus electromagnetic effect. That means here the attack takes away from the reagent. Fine? Now, as I told you, first was the electronic effect, and second will be hyperconjugation. Hyperconjugation effect. Now, what do you mean by hyperconjugation? Basically, alkyl groups, in this case the alkyl groups when bonded to pi bonds, alkyl groups when bonded to a pi bond, I'll give you an example. Take for example alkyl group CH3. It is bonded to pi bonds. This is pi bond. When the alkyl group is bonded to a pi bond, see, now we know this is C double bond C, so this happens to be an alpha carbon atom. As I have told you, this happens to be the alpha carbon atom. This is ene, this is a functional group, and this is the alpha carbon atom. If the hydrogen atom attached to an alpha carbon atom is known as alpha hydrogen atom. Now, here the alpha hydrogen atom plays a very important role. The alpha hydrogen atom, and this will become fine. Now, fine. Now, this will be H plus. So this is known as hyperconjugation. Means the alpha hydrogen atom, the shifting of alpha, the bond connecting this alpha hydrogen atom, there is a shifting of that particular bond shifting of that particular bond such that it then follows a shifting of the pi bonds, forms the shifting of the pi bonds, right? And the electron is released. So this is known as hyperconjugation. That means I can say there is a type of resonance undergoing. Again, then this will come here and this will go here. That means you can say this is a resonance type. Okay? Now, this type of electron released on the carbon atom due to the presence of alpha hydrogen atom is known as hyperconjugation. Now, greater the number of alpha hydrogen atoms, more is the stability. Sorry, more is the transfer of electrons. You can say delocalization. Delocalization means the electron is not localized to any specific place. Delocalization of electrons to be more precise, pi electrons. That means, can I say this is a sigma bond and this is a pi bond? Okay? That means I can also say it is a sigma pi conjugation. It is also known as sigma pi conjugation. Sigma pi conjugation. And also it is known as no bond resonance. No bond resonance. Why? No bond resonance because there is no bond between the alpha carbon atom and the hydrogen atom. That means here this and this, there is no bond. So it is known as no bond resonance. No. Fine. If this is alpha carbon atom, can I say there is 3 alpha hydrogen atoms? 3 alpha hydrogen atoms in the case of methyl. Similarly, if I take CH3, CH2 dash C double bond C, this I can say there is only 2 alpha hydrogen atoms, and in case of CH3 C CH3 H dash C double bond C, there is here it's only 1 alpha hydrogen atom. So can I say the presence of methyl group? The presence of methyl group makes the compound more stable as compared to presence of ethyl group as compared to propyl group. Fine. Because as we know, more the alpha hydrogen atom, more will be the conjugating structures. Take for example H dash C double bond C. Okay. First will be conjugating structure due to this, the second will be due to this, and the third will be due to this. That means as many number of alpha hydrogen atom, that many number of conjugating structure. 3 alpha hydrogen atoms, 3 conjugating structures. Suppose if we have C, double bond C, and comparatively here it is CS3. That means this is 3 alpha hydrogen atom, this is 3 alpha. That means I can say 6 alpha hydrogen atoms. That means there will be 6 resonating structure, conjugate resonating structure. So this will be more stable, because more the conjugating structure, more is the stability. That means more is the delocalization of electron. So can I say this, he is more stable than CS3C double bond C? So I think so now you might have understood type of naming in which an organic compound is named in a particular systematic way. Basically, there are many, you can say, two types of naming. One was the common name, or you can say trivial name. And the other one was derived name, you can say. Means it is derived from where? Okay. Now at this place, now IUPAC naming is implemented universally. Fine. You can say CH3OH. Its trivial name, I can say, its trivial name is methyl spirit. Take for example, methyl spirit, and its source is what? It was destructive distillation of wood. Fine. Similarly, CH3COOH. The trivial name was vinegar. It was, what was the source? This is the source. Obtained from vinegar. No. Take for example HCOOH. This is known as formic acid. Obtained from ants. Red ant. Right? Similarly. Right? For example, again, CH3, CH2, CH2, COOH. This is known as butyric acid. Butyric acid. It is obtained from butter. Fine. While naming a particular compound, 3 things are very important. First thing is the prefix, as I have told you regarding the prefix of functional groups. Prefix, then suffix, and the root name or the parent name. Prefix and suffix of a particular functional group, you can see it in the previous lectures. Now, what do you mean by root name? Root name is nothing else but the presence of carbon the presence of carbon atoms in a particular compound. You can say a basic unit that denotes the number of carbon atoms in the principal chain. Uh, Carbon chain, which includes functional group, right? Functional groups, if there is a presence of functional group, that means prefix and suffix come here, and the root name or the parent name depends upon the number of carbon atoms. For example, if there is one carbon present, then it will be known as myth. Myth, because it has come out from one carbon atom, means methane. Similarly, C2 will be known as eth. Yeah, ane is deleted. No, myth. Ane is deleted, then eth. Eth represents the root name, parent name, right? You can say root word or root name word. Then suppose similarly, now suppose there is C7, then it will be known as hept, H-E-P-T, because this form heptane. Fine. Similarly, if it is C10, then it will be dec or decane. We will start with first nomenclature of alkanes. Nomenclature of alkanes. You can say nomenclature or naming. First, what happens? We have to select a parent chain. Parent chain means how many carbon atoms it has. Then, second will be numbering of that parent chain. The parent chain, right? Now, there are certain rules which we have to follow while selecting it and also numbering it. Now, we'll go step by step. First, rule 1 is longest carbon chain. Longest carbon chain that is containing maximum number of carbon atoms. Longest carbon chain or maximum number of carbon atoms. They are known as parent carbon chain. Fine. Or we will say it PCC. Whenever I say PCC means parent carbon chain. Fine. Now, see, it is not compulsory that the longest carbon chain, not compulsory that the longest Longest chain has to be straight. That is, it can be even in a branched form. It can be also branched. For example, take for example C, 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 C. Okay, so the longest carbon chain will be 1, 2, 3. See, longest carbon chain, maximum number of carbon atoms. Suppose from here to here, if I go 1, 2, 3, 4, but here 1, 2, 3, 4, 5, 6. So for me, this will be the longest carbon chain. And this becomes a substituent. And this becomes the PCC. Four, five. Just take for example chlorine, and this is chlorine. Right? Now here if I go 1, 2, 3, 4, 5, or if I go straight, then it is 1, 2, 3, 4, 5. But if I go 1, 2, 3, 4, 5, that means if I go here down or if I go straight, it will be 5. So, but I will prefer 1, 2, 3, 4, 5, because here this has another two substituents. So the substituent happens to be given the more priority. Substituent happens to be given more priority. More the number of substituents, the preference goes to that chain. Fine. So this becomes the parent carbon chain because due to the presence of two substituent. If there was no substituent, then no issue. Whether you can go here or you can go here. If you go straight, then this will become the substituent, and if you go like that, then this will become the substituent, right? In such a way that the substituent gets the lowest locant number, right? The numbering along the PCC is done in such a way that the substituent should get the lowest preference, should get the lowest, not lowest preference, but the lowest locant number. Take for example 1, 2, 3 and 4. Take for example here there is a substituent, right? Now if I go from like that 1, 2, 3 and 4, at third position there is one substituent. If I go from here like that 1, 2, 3, 4, at the second position there is a substituent. So I will prefer going like that. That is 1, 2, 3, 4. That means it will be 2. Suppose if it is methyl, 2 methyl, and the longest carbon chain is 4. If C4, then it is butane, 2 methyl butane, 2 methyl butane, 2 methyl, 4 carbon atoms, so its parent carbon chain happens to be butane, 2 methyl butane. It will be not 3 methyl butane. This will be wrong and this will be correct. Fine. Two or more substituents are present in the parent carbon chain, then the lowest locant rule is followed with respect to alphabetical order. For example, 3, 4, 5 and 6. Here there is C and C. Now, the numbering is preferred whether I have to go 1, 2, 3, 4, 5, 6, or I have to go 1, 2, 3, 4, 5, 6. Now, this is nothing else but 2 carbon, that means this is ethyl. If this is 1 carbon, that means this is methyl. Now, the branch is first preference. First preference has to be always given to branch. If branching is given the preference first thing. So the branching is immediately on the second carbon atom. So it will be 1, 2, 3, 4, 5 and 6. But while naming now, so even though at second position it is methyl and third position is ethyl, but it has to be written. It has to be written as 3 ethyl 2 methyl hexane. To 3 ethyl because alphabetically E comes first and M comes afterwards. So 3 ethyl. Numbering we can give from here, but while writing the IUPAC name, we have to write 3 ethyl. Now you have to make it that whenever differentiating between you want to differentiate a number and an alphabet, always use an hyphen. Number and an alphabet. Number and an alphabet. Number and an alphabet has to be differentiated. Has to be differentiated by putting an hyphen in between. Right? So 3 ethyl 2 methyl hexane. Rule 4. Now comes rule 5. No, fine. If 2 or more similar substituent is present in the parent carbon chain, then they are represented by who? Those particular substituents are represented by di. If 2 are present, tri. If 3 are present, tetra. If 4 are present, and so on. And so on. Fine. Although the presence of this di, tri and tetra, D, T and this T is not considered in an alphabetical manner. Alphabetical manner is only given to the substituents, not the how many number of substituent. A substituent like methyl, ethyl, whatever, जो is Whatever is a substituent, it's given the first preference. But di, tri, tetra, this D, T, T are not given any preference. There is no such alphabetical order. For example, 2, 3, 4. Suppose this is C and on the same card. So obviously, sorry, this is CS3, this is CS3. Now naming, I'll do it from 1, 2, 3, 4. So how will I write? 2, comma 2. On the same carbon atom, when the same this is present, substituents are present, then it will always be written as 2, comma 2. This indicates when two numerical values are written side by side, then they are differentiated by putting a comma. 2, 2 dimethyl, 2, 2 dimethyl, and parent is 1, 2, 3, 4. 2, 2 dimethyl butane. 2, 2 dimethyl butane. 2, 3 dimethyl pentane. 2, 3 dimethyl pentane. Similarly, here it is. No. The naming, obviously I have to start it from here. And the second position is ethyl. Suppose I have the same thing. C, C. Here this is C, this is C. Here the second position is. The naming now. Here second position is a substituent. Here also second position is a substituent. But here there is a ethyl. And this is a methyl. And as per alphabetical, ethyl comes here. So I have to start the naming from here. 1, 2, 3, 4. Fine. So it will be 2 ethyl, 2 methyl, because there are two different substituents. Yeah, either here again 2 ethyl, 3 methyl. This is pentane and this is also pentane. Fine. If two or more substituent, take for example, this is chlorine and this is bromine. Then the numbering here is done from the, this is chlorine is represented by chloro and this is bromo. Then it's common, the numbering has to be done from here because bromo comes first alphabetically and then comes chloro. So it will be 2 bromo, 3 chloro butane. Fine. These are the 6 rules pertaining to alkanes. 6 rules pertaining to alkanes. Right? We will do a few examples. We will do a few examples. Just a couple of examples I will do it. No. Suppose fine. Now, if I take 1, 2, 3, 4, 5 and 6. If 1, 2, 3, 4, 5. This is 5 is pentane. This is 6 which is hexane. So obviously I have to take the longest carbon chain is this. Fine. Now at second position there are methyl. This is methyl and this is methyl. This is methyl and this is methyl. So I will say 2, 2 again. Now fourth position also is a methyl. So 2, 2, 4 4 trimethyl. See, 2,2,4 it is written because all the three substituents are same. If it might be some ethyl, then I will not like that. Then I will write 2 dimethyl 4 methyl, like that, right? If the substituent was ethyl, for a ethyl substituent. But for this, it is 2,2,4 trimethyl, 2,2,4 trimethyl hexane. Similarly, fine. The naming, suppose 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Right? Now, here I can do it 1, 2, 3, 4, 5, and 6. Right? Now, so then I can say 3, 4. This is 2 carbon. That means this is ethyl CH3 CH2. This is CH3 CH2. 2 carbons. That means ethyl, 4 ethyl hexane. 2 chloro hyphen 4 hyphen ethyl hexane. There is no, it is a continuity. It is a continued 4 ethyl hexane, because within alphabets there is no hyphen or a comma, anything. It's in continuity. So 3 chloro 4 methyl अपना 4 ethyl hexane. Now, suppose take this. Fine. No, I will take 1, 2, 3, 4, 5. So I will say it is 3, 3. This is 1 carbon. This is second carbon. So ethyl 3, 3 diethyl, because here also ethyl. 3, 3 diethyl pentane. Fine. Now, so we have seen some few examples of it. Like that, many examples are there. Okay. So we have done at least a basic of IUPAC name nomenclature of alkanes. I think so. It's very easy. Just revise, and these are the basic rules. Then in the next lecture we will see the nomenclature pertaining to alkenes and alkynes. Nomenclature pertaining to alkenes and alkynes. Right? What happens in terms of cyclic? Suppose there is a cyclic alkane. And this is CH3. So it will be 1, 2, 3, 4, 5, 6. So it will be 1 methyl cyclohexane. 1 methyl cyclohexane. Suppose so this will be 1, 2. It will be 1 ethyl cyclopropane. Similarly, it will be 1 propyl. Similarly, if I take this, now here it's very, up till now we saw 1 ठीक है, 2 and 3. Similarly, 1, 2 and 3. First position there is a propane. Here you can see here there are 2 carbons, and propane, cyclopropane, there are 3 carbons. Here also 3 carbons, and here also 3 carbons. But here you can see 3 carbons, but the attach 1, 2, 3, 4. So what I, if the cyclic carbon atoms are greater or same than the substituents, then they are parent carbon chain. That means here the 3 carbon atoms of a cyclopropane and here only 2. So this is considered to be a parent carbon chain. Similarly, here 3 carbon atoms and 3. So this is considered to be a parent carbon chain. Now what is the scenario here? Here there is 4 carbon atoms and this. In this case, the PCC turns out to be this, and this becomes a substituent. That means to become a parent carbon chain, your carbon atom has to be more than the chain attached. Here the carbon atom, here the chain attached has carbon atoms less than the other straight chain. So this happens, so this becomes a substituent. So 1 cyclopropyl butane, 1 cyclopropyl butane, because that means butane becomes a PCC because it has 4 carbon atoms, that is greater than the substituent, and cyclopropyl is 3 carbon atoms, so this becomes a substituent. So more carbon atoms then it will become a parent carbon chain, and lesser will be the substituent. Here there is less carbon atom as compared to the chain attached, straight chain attached. If similarly 6 member. See 1, 2, 3, 4, 5. Still here this is 6 and this is 5. So this happens to be the PCC. And this is the substituent. But the moment 3, 4, 5, 6, 7. Here there is 7 carbon atoms and this is 6. So this becomes the PCC and this becomes the substituent. That means more the number of carbon atoms, with respect to each other. Whosoever has a maximum number of carbon atoms attached to the ring will become the PCC. Fine? Okay. So now we'll take a last example of this case. Suppose it is this. Fine? Now, the naming will be, since here there is branching, 2 branches are there. Here obviously there is single branch. Branching has to be given the first preference, but here there is 2 branches. So this is 1, this is 2, 3, 4, 5, 6. We can't go 1, 2, 3, 4, 5 and 6. Here because the second branching is immediately here, so the numbering has to be go there. So it will be 1 ethyl. Here this is also methyl and this is methyl. 1, 2 dimethyl cyclohexane. 1 ethyl 1,2 dimethyl cyclohexane. What? Cyclohexane. So I think so you might have understood now. This, as I told you, this is basic IUPAC nomenclature of the alkenes. In the next lecture, we will see regarding alkenes and alkynes. This was alkane, and that way now next lecture we will see alkenes and alkynes. So I think so you should go through the complete lecture, and you will have some background of what IUPAC nomenclature. I hope you have understood today's lecture, and I just request you, if you have any doubt, you can just write in the comments and ask the question to me. I'll surely reply. So let me take a leave now. I will approach you in the next lecture by the topic which I have told you, right? So thanks a lot. Thank you. Thanks a lot.